Hey everyone! Welcome back to the channel. Today, we're diving into a topic that might sound a bit niche at first, but it's rapidly becoming one of the most critical technologies driving smart vehicles, robotics, and AI at the edge. We're talking about FPGAs, Field-Programmable Gate Arrays. I know, not exactly a household term. But by the end of this video, you'll understand why FPGAs might just be the brains behind the machines you'll see on highways, construction sites, and factory floors in the years to come. Let's start with the bigger picture. From sleek Teslas zipping down the freeway to autonomous mining trucks working deep in the outback, electrification isn't just a trend, it's reshaping the entire logic of how machines move and think. Electric vehicles and heavy-duty off-highway machines rely on inverters and power converters. These components translate battery power into usable motor energy, enabling smooth starts, precise torque control, and regenerative braking. But hardware alone doesn't make these systems smart. What really matters is the controller, the system that makes decisions in real time. And that's where FPGAs come in. Historically, most controllers relied on MCUs, microcontrollers, or ASICs, application-specific integrated circuits. But as electric and autonomous systems became more complex, these approaches began to hit bottlenecks. Limited processing speed, especially for single-core MCUs. High latency. Lack of flexibility when requirements change. In contrast, FPGAs offer customizable logic blocks, parallel processing, huge win for performance, ultra-low latency, ability to evolve alongside rapidly changing tech. That's why more and more companies are ditching traditional microcontrollers in favor of FPGAs, especially in mission-critical systems like vehicles and industrial machinery. Let's take a real-world example. Imagine a massive autonomous excavator by Komatsu or Caterpillar. These machines need to coordinate multiple motors in real time. The main drive motor and steering motors working in tandem. The digging arm and blade operating simultaneously. Real-time torque adjustments depending on terrain slope or wheel slippage. With an FPGA-based controller, you can implement PID control, fuzzy logic, and AI-assisted decision-making, all within microseconds. This isn't theoretical. These systems are already being deployed, enabling machines to respond smoothly and intelligently in environments where milliseconds matter. Now, picture a self-driving mining truck navigating a remote site with no internet connection. How does it detect landslides, fallen rocks, or human workers entering its path? Here's the setup many companies use today, combining NVIDIA Jetson modules or Xilinx Crea with FPGAs. Cameras plus LiDAR feed raw data. The FPGA handles sensor fusion and pre-processing. A quantized AI model, like a CNN, runs directly on the FPGA. Based on the output, the vehicle's logic changes its path, slows down, or stops instantly. All of this happens without the cloud. That's true edge AI, reliable, fast, and secure. Now let's talk about what's happening inside your next-gen passenger car. ADAS is Advanced Driver Assistance Systems, rely on processing massive streams of data from cameras, radars, and ultrasonic sensors. Lane departure detection. Pedestrian and object recognition. Adaptive cruise control. Real-time video stitching for reverse cameras and 360 degrees view. Each of these needs split-second decision-making, and FPGAs excel here. They can run AI inference directly on the hardware layer while managing traditional motor and actuator control. Some startups are even integrating FPGA-based AI modules into construction vehicles, allowing them to recognize site conditions and hazards even when Wi-Fi or 5G isn't available. Batteries are the lifeblood of EVs, and managing them properly is a science in itself. The Battery Management System, BMS, does much more than just showing you charge percentage. It has to balance voltage across cells, monitor temperatures and prevent overheating, predict failures and isolate faulty modules. Using FPGAs here provides serious benefits. High-speed analog-to-digital and digital-to-analog conversion, ADC and DAC. Multi-module control with parallelism far beyond MCUs. Native support for multiple protocols, SPI, CAN, I2C, all at once. Even in harsh temperature extremes or rough terrain, FPGA-controlled BMS ensures stability, safety, and real-time response. Let's go from vehicles to the factory floor. In advanced manufacturing, like semiconductor plants or surgical robotics, timing and accuracy are everything. Companies like TSMC and Boston Dynamics are already using FPGA-powered controllers for real-time feedback loops paired with reinforcement learning. Micrometer-level precision using sub-millisecond FPGA control. Instant correction based on visual input, like detecting defects or misalignment. FPGAs process sensor input and update actuator commands without software bottlenecks, something traditional CPUs can't do fast enough. Today's FPGAs are evolving fast. SoC integration, FPGA plus ARM CPU on the same chip, e.g. Xilinx ZWNQ series. AI native support, built-in acceleration for frameworks like TensorFlow Lite. Model-based design, engineers use tools like MATLAB or Simulink to drag and drop logic blocks, HDL code is auto-generated. That means FPGA development is becoming accessible to software developers, not just hardware engineers. And get this, some companies are building no-code FPGA compilers, aiming to make logic design as intuitive as building with Lego. Of course, no technology is perfect. FPGAs do have a few hurdles. The challenges include high power consumption, difficult to learn HDL VHDL, and less efficient for mass production. But the good news is that the ecosystem is working fast to solve these by using low-power FPGAs, e.g. Intel Max, high-level synthesis, HLS, and combining with ASICs after prototyping. FPGAs are no longer just embedded control tools. They're becoming the central nervous system of next-gen intelligent machines. As AI models grow smarter, real-time requirements grow tighter, and safety becomes non-negotiable, FPGA-based systems offer a unique advantage, one that bridges hardware precision and software flexibility. Whether you're in automotive, industrial automation, robotics, or AI, now's the time to learn about FPGA. It might just be the future of dynamic systems. If you're working with embedded systems, edge AI, or self-driving technology, drop a comment below. We'd love to hear how you're using FPGA, or what you're struggling with. And as always, don't forget to like, subscribe, and hit that notification bell. See you in the next video.